Hi there! This is the second part of my review of the modules sent kindly by PN Lab. In the first part I was looking at the NanoBug, a nice and very efficient bug converter. Today I'm focusing on the FlexTrip, which is an electronic fuse. You actually get two FlexTrip modules in your order, making this much more affordable than other electronic fuses. This also hints at a common use case, namely power O-ring, which needs at least two modules, and of course I will try this as part of the review. As before, the pin headers and terminal blocks are in separately sealed compartments. So what is the FlexTrip? Here's a summary and you can pause the video to read it. The important points are that it's both a diode and a fuse configurable between 0.5 to 5.5 amps. The fuse latches, so when it trips you have to manually reset it, which can be done by digital signal or the reset button on the board. Also note that while the board is in forward direction, it can deal with anything between 3 to 22 volts. The protection in reverse direction is only up to -12 volts. Configuring the current limit for the fuse is done using solder bridges. You have a choice of 6 currents from 0.5 to 5.5 amps. By examining the PCB, I found that the chip implementing the E-fuse is the Texas Instruments TPS249474LRPW, and the datasheet of that chip reveals the formula for the resistor R-lim determining the limit. You can see the 6 resistors on the left of the solder pads. I calculated the values for the 6 settings, and by measuring the resistors it turns out that this formula is indeed the correct one. While you are supposed to add only one solder bridge, I included in my table values that you can get by putting in 2 solder bridges, which effectively puts the resistors in parallel. This is quite neat, and with this trick you can configure any current value from 0.5 amps to 5.5 amps in 0.5 amp steps. For fuses that should be sufficient granularity, given that both the chip and the resistors have some tolerances. For my test I decided to configure the board for 1 amp, so I put a solder bridge on the pads marked 1A. With that done, I added the terminal blocks. For the pin headers I used my own angle variant instead of the straight ones that came with the module. Actually, in many cases you don't need adding the pin headers. It's really just DC in on one side and DC out on the other, which is exactly the way I'm planning to use this board for its first test. This test uses the module without any other connection to the pin headers, so we see what the basic board does on its own. I connected the meter on the left to show the output voltage and the one on the right to show the current. The load is this big 12.5 ohm rheostat. At 10 volts and moving it all the way to the left, I can select currents as low as 800 milliamps, increasing as the slider is moved to the right. Watch the current on the meter on the right as I increase the load. Moving the slider is quite hard going despite the greaser added to its rails. Just about at 1 amp the fuse trips and the voltage and current drops to basically 0. This is what you would expect. Slightly unexpected is that without touching the slider position I can press reset on the module and the output becomes active again, at actually a tad above 1 amp. In fact, as I continue to move the slider to the right, watch the voltage and current readouts. As I move to lower the load resistance, the module actually goes into current limiting. The current remains at roughly 1 amp and instead the output voltage is dropped. This continues until the output voltage has dropped nearly 2 volts, but then the module kills the output again. Can I recover it using reset? Yes, it comes back, but only very briefly, and then the fuse trips again. Trying reset again and the same thing happens. Apparently this is as far as the module will go. Probably the overheat protection is now active. Okay, let's reset this setup by moving the rheostat back to the left. Pressing reset brings the output back because now the current is just a tad over 800 milliamps. If I take a lead and shorten the output, the fuse trips as expected. No attempt at limiting the current. I was curious if the module provides any type of undervoltage protection. The lowest input voltage is specified as 3 volts in the FlexTrip datasheet. dropping below 3 volts and the output is still going, but at about 2.5 volts the output is turned off. Interestingly, raising the voltage over that threshold again and the output is back without having to press reset. Let's just verify the reverse polarity protection by swapping the leads on the power supply. Yes, it works. The output remains off. And reversing the leads back to the correct polarity, and everything is back to normal. As I mentioned earlier, the chip doing all the magic is from the TI TPS25947XX family, and it's absolutely tiny. It took a lot of magnification to get a clear image of the marking. 2ACH. This code resolves to the TPS249474LRPW and selects the following options. The overvoltage protection can be adjusted using a resistor divider. The overcurrent protection is the circuit breaker response instead of current limiting. There is a power good signal and the threshold when it should be on can be adjusted. And finally, if a fault is detected, the chip turns off and latches the state until reset manually. This opposed to other chip variants which try to recover automatically. The availability of some chip features like overvoltage protection, slew rate control and transient blanking timing depends of course on the way PN Lab designed their FlexTrip. Apart from the resistors for setting the trip current, I did not try to reverse engineer the FlexTrip schematic, because there's more stuff than just this TI chip, and I could not confirm what all these actually were. For sure, overvoltage protection cannot be implemented as the FlexTrip allows the full range of voltages. Somewhat baffling to me is the current limiting behavior we observed, as my understanding of the TI's datasheet describes this for other chip variants and not the one we have here. But I guess the chip internals are probably so similar that it may be active even in the circuit breaker variant. Some notes of the additional connections available on the board. These descriptions were missing in my FlexTrip manual, but when you see this video, PN Lab has probably added them in. PG or power good is just an open drain output. VCC and PG are actually connected by a 384K resistor, but VCC itself is only going to that input and nowhere else. It is possible to connect it to in plus, which then creates a pull-up for the PG output. The RST input is going to the gate of a MOSFET. If it goes higher than 3 volts, it signals to the chip to turn the output off. And ground is connected to in minus and out minus. I repeated some tests to capture the timing using an oscilloscope. Here is the power up behavior. The yellow trace is the output current and the green trace the output voltage. Ignore the VRMS readouts. I should have disabled that since this is a DC setup. Since the horizontal deflection is 1 millisecond per division, we have about 10 divisions or 10 milliseconds for voltage and current to ramp up. So the application gets a controlled soft start provided by the FlexTrip. Here's the case of me shorting the output with a lead similar to what you saw earlier. The first observation is that touching a banana plug on another is not a very solid connection, hence we have all this jitter up there. Secondly, the chip immediately limits the current to stay just below 1 amp by reducing the output voltage, which is the green trace, to basically nothing. And finally, even though I kept my banana lead connected for at least a second, the whole thing is over after about 80 milliseconds when the chip had enough and turns the output completely off. Here's the scope picture of the test where I moved the rheostat slider to the right until the fuse tripped. You can see that the yellow trace rises to the 1 amp limit, which is right at the top of the screen. The trace is not smooth because the slider is moving fast over the rheostat windings and I moved it quite fast in this test. But notice that the green trace is steady right until the fuse trips, staying close to the second division line, which is 10 volts, no sign of current limiting. The slider is now somewhat beyond 1 amp. Let's see what happens if I press reset, just reconfiguring the scope trigger first. Okay, here we have the usual 10 millisecond ramp up, but now we are full into current limiting. The yellow trace is basically hard at the 1 amp limit, and the green trace of the output voltage is significantly lower than its previous value. Current limiting means, of course, that the chip is now turning the voltage difference between input and output into heat, and if nothing else, the overtemperature cutout will limit how long this can continue. Here is the case where the chip automatically trips after about 1.5 seconds after the current limit mode was entered. How long the chip can handle the current limiting mode depends on the current. For each of these shots, I have moved the rheostat slider more to the right, and you can see that the time gets shorter at every try. But we must still be in the region below 2 amps, because the TA datasheet also states that if the current rises beyond 2 times I limit, so 2 amps in this case, the chip assumes a short circuit and trips immediately. The current limiting mode is useful if the load causes a significant inrush current. An easy way to test that is to connect a massive capacitor to the output. In this case, 2 4700 microfarad caps in parallel to close to 10,000 microfarad. By the way, the 1 ohm resistor you see in the foreground is how I measure current with a scope. The probe simply measures the voltage drop over the 1 ohm resistor, and 1 volt measures here means 1 amp current. To use the screen better and improve resolution, I moved the zero line for both traces to 1 division from the bottom. For comparison, here is the power up behavior without the capacitor. It's the usual, a 10 millisecond ramp up, after which the green voltage trace is close to 10 volts and the yellow current trace close to 800 milliamps. After connecting the capacitor, I rerun the power up test, quite a bit different. The yellow current trace now goes over the 800 milliamps and is eventually limited to 1 amp. The green voltage trace ramps up slowly as the capacitor charges. Eventually, after about 180 milliseconds, the system reaches a steady state with the current and voltage reaching the values they had without the capacitor added. And here's the same scenario without FlexTrip. With an unregulated input, the inrush current would be even higher, but the bench power supply limits it to 10 amps. This clearly shows the value of the FlexTrip module. Since the FlexTrip module acts basically like a diode, you can wire the outputs of 2 or more together for power sharing, as I have done here. The combined output feeds the rheostat load resistor. Just a quick explanation. If this power supply shows a current with all decimal points, it means the output is actually off. No current is flowing. The value shown is instead the current limit, which I have arbitrarily set to something well above 2 amps. Next, this is a dual power supply, but as you can see from the mode selection, both halves operate independently and fully insulated from each other. With that out of the way, if I arbitrarily switch the output of one of the supplies on, it delivers the full current of about 820 milliamps through its FlexTrip to the load, as you would expect. Turning the second power supply output on, and now it delivers about 200 milliamps, while the power draw on the first drops by the same amount. The reason that the current split is not exactly half is because the left power supply uses thinner wires to feed its FlexTrip, so there is a higher voltage drop. I can make the load split symmetrically by reducing the voltage of the first power supply or increase the voltage on the second. There, now we have roughly a 50% split. Turning either power supply off and the other power supply takes over, delivering the full current, and if both are available, the split is again 50%. So far so good, but remember both FlexTrips are actually set for 1 amp trip. With the power share running, I can now lower the load resistance and increase the current quite dramatically. The increased current makes the voltage drop due to the thinner wires on the left more pronounced, but I can rebalance the load. This time I use the method of increasing the voltage on the left. Now we are feeding 2 times 800 something milliamps into the load, in other words 1.6 amps, but since the current is going through each FlexTrip is still below the trip current, this type of power sharing can overwhelm the load if it wasn't designed to handle 2 amps. This resistor is now getting nicely warm. What will happen if one of the supply fails? The other supply tries to supply the full current of 1.6 amp, which trips its FlexTrip set to 1 amp, so the load has now lost all power. Turning the failed power supply back on doesn't help, because trying to deliver 1.6 amp now trips the fuse in its FlexTrip. Is there any way to recover without reducing the load? I tried pressing reset on both FlexTrip modules simultaneously, and this worked the second time I tried it. Actually, the ramping up and current limiting we saw earlier helps here to make the timing of the simultaneous reset less critical. In practice, for such an application, you would wire the reset input of the FlexTrips together and drive both from a common switch. That was power sharing, also known as power ORing. It is used, for example, in servers with redundant power supplies that are hot swappable. Now we move on to priority power multiplexing. As before, the outputs of both FlexTrips are still wired together and each is fed from a power source, but now one has priority over the other. They are not sharing the load current, instead the priority source provides the full current, and only if it fails, the second FlexTrip takes over and provides the full current from its source. The sources could be a mains power supply as a primary and a backup battery as an alternative. If mains power is available, you want the load always to use that source, not to drain the backup battery unnecessarily. There are two caveats with this. Firstly, you should limit the voltage to 12 volts max to not overload the inputs of the pin header section. The second one is that the backup voltage must be smaller or at most equal to the mains voltage. In my tests, if the backup voltage is more than a volt higher than the main voltage supply, then the FlexTrip for the main supply will not resume feeding the load when the main supply comes back. In this circuit, I use the PG or power good signal from the main FlexTrip to drive the reset pin of the backup FlexTrip. As long as the priority FlexTrip has good power, it holds the reset of the other one high, forcing it to be off. Since the PG is an open drain, you need a pull-up resistor to get a signal that can be used. In my test setup, I actually connected the ground pins of the two FlexTrips with each other, forgetting that this was unnecessary as the two out minus of both boards are already connected to each other at the load. I briefly want to mention this setup. I should not need my 10K pull-up resistor. As discussed, connecting VCC of the main FlexTrip to in plus provides a 384K pull-up, but in my test this did not work. While it prevents the backup FlexTrip from running while the main supply is available, it did not take over when the main supply failed. I suspect the pull-up resistance is too high. When I replaced my 10K with a 470K that was at hand, I saw exactly the same behavior. Here's my setup. The top FlexTrip is for the main supply. As I said, ignore the black wire going from the rightmost pin header to the other FlexTrip. That is the unnecessary ground connection. The gray wire is the PG signal, which connects via a yellow lead with alligator clips to a white wire and a 10K resistor. The other end of the 10K resistor is connected to in plus of the main FlexTrip. And the white wire goes to the RST pin header of the backup FlexTrip. When I turn both backup and main supply on, only the meter on the right acting as main supply showing current as it has priority. When the main voltage fails, the backup takes over and supplies the current. And when the main voltage comes back, the load current switches back to the main supply. What we really care about is, of course, if the switching between main and backup causes any interruption to the load. In this setup, the yellow trace is the voltage to the load from the two combined outputs of the main and backup FlexTrip boards. The green trace is the main in plus voltage. As you can see, the yellow trace is not disturbed even with a 2 millisecond per division time resolution. And after I configure the scope to capture the return of the main voltage, the same is true. There is a slight increase as the main voltage was slightly higher, but nothing else happens. And that concludes my review of the FlexTrip modules. Thanks again to PN Labs for sending these in. I'm always in two minds about E-fuses. I don't think many people use them when developing and testing circuits on the bench. At least I don't. I find it far easier to just hook up the circuit to my bench power supply with easy adjustable current limit and maybe overcurrent protection. For me, the moment when an advanced E-fuse like the FlexTrip becomes very useful is when you leave the protection of the development workbench and install a circuit into a real device. Now you have to deal with the harsh world of real power supplies that can easily fry an expensive design if something goes badly wrong. This is where for me using FlexTrip or the even more advanced protection and power management modules offered by PN Labs makes total sense. I leave a link to their site in the description of the video. They are also selling via the Electrons marketplace, which is more convenient if you are in the EU or the UK. At present the prices were about £15.50 or 18 euros for a pack with 2 FlexTrips. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.